think it will be better.
Yeah, okay, we can do it in this way.
So, okay, then I'll send you an email in I don't know, maybe today, maybe tomorrow.
Yeah, it's your decision. After the presentation or
Okay.
after my lecture, you can send it, or during whatever. Then I will send you the lecture in as a PDF data. Okay.
Okay, thank you.
Then let's start with the lecture. Welcome, and I will give you a short summary of what we have discussed in the last session. Means we talked about antenna measurements, and you see here the first slide. I will make it full scale, okay? And the simplest way to measure an antenna, you can see it here in this slide. It's very simple. You mount the antenna for illumination. I change to the laser pointer. You can use a tower, let's say, made from plastics or not metallic because of reflections. It must be from material which has no reflections, and timber or whatever for the illumination antenna. On here, our antenna under test. On the other side, what you have to ensure is the distance between both antennas, so that you are in every case in the far field with the antenna under test. This is the main condition what you have to keep in mind, or what you have to ensure. The conditions, again, it's shown here. The large D, capital D in square, it's here the main, let's say, cross-section distance of the antenna under test. It's measured between the outer metallic parts, and means this distance must be much larger than these conditions. The condition itself fulfills only here this phase error, but this is very large, the phase error, and this came from earlier antenna measurements, maybe 50 years 50 years ago in this area. Okay. Then we discussed about the ground reflection here. It's clear if you have an antenna under for illumination, antenna under test, then in a certain distance from the ground, you cannot make your towers or your masts infinity in height. It's impossible. You have in every case a certain height, and in this case you also have a ground reflection, and this makes an uncertainty in the measured antenna patterns. We can, let's say, show two different cases. In one case, if you want to determine the elevation pattern here, you have to turn the antenna in this direction, for instance, or this direction, doesn't matter. But in a certain measurements scenario, the main beam looks directly to the reflection on ground, and this makes a problem. And on the other side, if you turn the antenna further so that, let's say, a zero occurs in direction of the reflection, then there's no influence on the pattern. And so we discussed how we can roughly determine, let's say, the magnitude or the value of the reflection. And we have to find the two, let's say, critical points, the maximum and the minimum, and then you can say, okay, this is the mean value between these two values. What we have to consider as an error in pattern measurement because of the ground reflections. But you can also ensure that the ground has a very, very low reflection coefficient. Normally in nature it's given by grass and such things. Or also you can apply here absorbing material, and we discussed this also in the last session. To avoid ground reflections, you also can choose this measurement setup. The antenna on the test is on the top of the tower. Again, non-metallic material, timber or whatever, plastic, and here on the ground you have the transmit or illumination antenna. And so you can avoid any ground reflections. But this setup, it limits, let's say, the dimension of the antenna to measure, because if you have a tower with a certain height, then okay, then this distance you can make a little bit larger by changing this distance, but normally you are limited in the measurement area. Okay, this was the discussion regarding the influence of the ground reflection. Then another measurement setup is the so-called compact range test setup. It's shown here. The main problem is to realize this special formed reflector, which has to consider the pattern of the illumination antenna itself. Then it's clear all rays coming from the illumination antennas must be reflected in such a way that the rays are here in parallel or collimated. And this is the problem. But if you can realize such a shape, such a reflector, then you have the advantage that the measurement distance has not to fulfill this far field conditions, because you have here in principle, let's say, a plane wave which goes to the antenna under test, and so you can make the distance between the reflector and the test antenna very, very short, and so you can save place where you can bring this arrangement into a large room. But in every case, on this side here, there also should be an absorbing wall. Means the wall should not realize large reflections, because then we have here an interference between this main reflector, because it has a higher reflection coefficient, metallic, and what comes from the wall. So we have to avoid this. The other possibility is shown here again. It's the compact range now inside the room, and here you can see also the walls here are covered with this absorbing materials or pyramids from foam. Foam is filled with carbon particles, and I told it also with ferrite particles. So the electromagnetic wave, it's very strong absorbed. Another possibility was shown here. This is, it looks like also the measurement machine itself looks like a scanner, and it works also like a scanner. You have inside a probe, for instance, motor driven in the XY direction, and this probe detects the electromagnetic field coming from our antenna under test. And normally for this measurement setup, or for this measurement method, we use more or less planar antennas, for instance, microstrip antennas, microstrip arrays, because this type of antenna, it's from its nature very close to this compact measurement setup. But in this case, we cannot hold the far field conditions, so we have to apply, it's shown here, a fast Fourier transform algorithm, and from the near field detected magnitudes and phases, then we can make a transformation to far field patterns. Means the measurement results are not directly recorded, And we have between measurement results and the wished pattern, the wished results, we have a mathematical apparatus, a fast Fourier transform algorithm. And this we have to consider so that we cannot directly check or prove if the antenna test is, for instance, correctly located and so on. We can see it only after the measurements. Here I only want to show you how to determine the gain of an antenna under test regarding to the well-known gain of a reference antenna. And here you can see let's say an outside standing room for such a anechoic test chamber. It's comparable with this scenario of the compact test range, but this is the same what we have seen in the first slide. Means if you go to nature, we can remove all this absorbing walls, but if you go inside a building with a very large room to hold the far field conditions, we have also here two dielectric masts, dielectric towers from, for instance, plastics or timber. And so we have around the antenna test, let's say, a special area which is named quiet zone. It's not let's say a special sink inside the room. It's only determined by the given maximum errors which are allowed regarding the magnitude and regarding the phase differences to the, let's say, ideal case. And here it's, for instance, given with a magnitude error of 0.2 dB and a phase error of about 0.5 degree. And this determines the so-called quiet zone. You can allow larger errors for this so-called quiet zone or smaller errors, depends on what you want to achieve or what you want to document or to save in your technical description. Yeah, and we started in the last lecture with the fundamentals of noise measurement, or about noise in the electrical setup of a receiver or a receiving system, or let's say a communication system. We have on one side the transmitter, and on the other side we have our receiver together with the antenna. On the transmitter side we also have an antenna, it's clear, but the noise behavior on the receiver side is in this case much more important regarding to the transmit side. And I showed you here some examples regarding the so-called carrier to noise ratio. Means the carrier, it's a sinusoidal signal which is modulated with the wished information. And here there was shown several different modulation schemes. For instance, a very simple one was the BPSK, means it's only a phase switch between, let's say, plus and minus 180 degree, extremely opposite phase, and then or plus minus 90 degree. The difference is, sorry, the difference must be 180 degree. Okay, plus minus 90 degree, and here we have the so-called 4 PSK. Then we switch between 4 different phase changes. For instance, 0, 90, 180, 270, and 360 degree. Between these 4 phase states we can switch or modulate. This is all these modulation schemes are digital modulation schemes. Then, for instance, we have the so-called 8-peer scale. Then we have 8 different phase states, means every state is 45 degree difference to the other state. And it's the same like here, but with smaller phase distance. In this case, 90 degree, and here 45 degree. And here we have, this is the first scheme, which also modulation in the magnitude. We have 2 different magnitude states additional to the to the 8 phase states. Together, it's 16 quadrature amplitude modulation. And here we have 16 phase states, means again if the phase difference between these two is halved, it's only 22.5 degree. This is, let's say, the ideal case, but in practice, okay, it's smaller or larger, depends on the error. Yeah, this is here the probability of error, or the error rate, and we can see the higher the modulation degree, or the higher the density of modulation, we can see here the higher the so-called carrier to noise ratio has to be. For this very primitive modulation scheme, 2 different phase states, switching 90, minus 90 and plus 90 degree between these 2 states, then we need for this error rate of 1 million, about let's say a carrier to noise ratio of only 12 or nearly 12 dB. For the higher schemes, for the same probability of error, we need much higher signal or carrier to noise ratio. We also can say signal to noise ratio. The behavior is the same, maybe the scaling is a little bit another if you say signal to noise ratio, because also the, let's say, the bandwidth and so on plays a special role if we speak about signal to noise ratio. Yeah, this is explained here on the first slide when we started with this in the last lecture. And now we want to finish the discussion. I also tried to show you where or who has introduced, let's say, a figure of merit for this, for this noise behavior. We need a figure of merit to measure or to determine what happens inside of our receiver, what happens together with the antenna and the receiver. And we can say, if we have a very good antenna, means an antenna with very low losses, an antenna with a high gain, then we can achieve in every case a very good signal to noise ratio, or in other words, a good noise behavior of our receiver channel, of our receiver chain. Chain means it's a cascade of different blocks for a receiver, starting with the antenna, preamplifier, the next block, a mixer, for instance, with an oscillator as the next block, then intermediate frequency amplifier, and then the demodulator, because all signals must be modulated with the information we want to transmit. Okay, then this man, Harold Fries, in the 1944, I guess, introduced this relation here, and this is valid until now, and it's nothing else than a quotient of a quotient. It's this signal power divided by the input noise power as one quotient, in the nominator. In the denominator, we have the output signal divided by the output noise power. And now how we can, to determine this, let's look to this part. Here we have the same relation, okay, but what is the output signal? If it goes through our amplifier, for instance, then we have the large G, capital G, means the power amplification of our amplifier. This is the large G, for instance, 10 times or 10 dB. SI is our input signal power, and this is now divided by not only the input noise power amplified by G, what is seen here, but we have here in this bracket, this is what we expected. This is G multiplied by the input noise power. But here we have a so-called N added or N additional. This is a noise power coming from our amplifier itself, from the inner noise behavior of an amplifier. I already mentioned this in the last lecture, means that we have, because of the current flow of the active elements, for instance, transistors or tubes or whatever, we have an additional noise, additional noise behavior of these active parts, and also depends from the environmental temperature, means this is a contribution of thermal noise, and both parts together are expressed with this additional noise power coming from our active device, coming from our amplifier. For instance, if you only look to for instance, an amplifier to make our discussion a little bit convenient. Okay, then we rearrange the formula. We can write the formula in such a way, because this is the denominator in the denominator. It's now the nominator here, you can see it. Then we have here in the nominator the noise power, the additional noise power, plus the input noise power. In our case, it's in every case, or should be in every case, the input thermal noise power coming from the real part of the impedance of our source. If the source, let's say, is a real resistance in principle, for instance 50 ohm, then we have only the real part as 50 ohm. We have no let's say reactive part, but from theoretical point of view, we mean only this is this thermal noise power, it's only coming from the real part of the impedance of our source generator or antenna. Also, our antenna is has reactive parts, has imaginary parts. We already mentioned this in one of our first lectures. So here is the summary of this, what I mentioned now. This NA is the noise added by our device under test, for instance, an amplifier. The G is the signal gain, power gain of the device under test, for instance, an amplifier. And now this T0, this is very important to keep it in mind, is the source temperature of, and this is very important, because if we use another source temperature, then all the noise figures we determine are not valid or not correct. This is related to source temperature of the real part of our impedance of the source of 290 Kelvin. It's in Celsius about 16.8 or about 16.8 degrees Celsius. In earlier days, let's say this was the temperature in a writing room, for instance, in 200 years ago, the people were standing on a table or on a pult, writing down and not sitting. And standing, the room temperature could be lower than what we have nowadays. Now we have room temperature, let's say 23 degree, 22, 23, up to 25. This is the room temperature nowadays if you are sitting and writing. But in earlier days, the people were standing, and from this time, this rule or this temperature comes from 16.8 degrees Celsius. It's about this value. Okay, nevertheless, I have to repeat it. This is the base of all the measured noise figures. I switch back. Sorry. Okay, then we will see it here on the next slide. And now this is our base definition, and in the input noise power, we can find this T0, this source temperature, and this is shown here in this formula. It's the same formula like here, but only we have look more in detail in this part here. This is our power gain of device under test, and now we can see here what is the input noise power, and this is shown here. This is the small k Boltzmann constant, then our temperature of the source, this value, and the bandwidth of our device under test, not the bandwidth at the input of the device under test, because this makes no sense, because the noise power at the input must go through the device under test, so that it has to pass the internal bandwidth of our amplifier. Let's say the most amplifiers, also broadband amplifier, has a more or less low pass characteristic, or in a lot of cases, or a band pass characteristic. Means the so-called DC amplifier has a low pass characteristic, and the let's say RF wideband amplifiers has also in a lot of cases a band pass characteristic. Means there's at lower frequencies a high pass character, and at much higher frequencies has the low pass character. And so we can determine in every case, nevertheless, if it's a low pass, or nevertheless it's a high pass in connection with a low pass, means it's a band pass. In every case, we can determine this bandwidth. In one of our last slides, I will show you how we can determine this bandwidth. And I will give you now, let's say, the keyword for this bandwidth. It's the so-called equivalent noise bandwidth, or equivalent noise behavior. Means this determined bandwidth has to follow a special rule, and I will later explain you how to fulfill this rule to determine this bandwidth. And now you can see it here again in this marked words. Boltzmann constant multiplied by our source temperature multiplied by the equivalent noise bandwidth. This is our input noise power as a reference for the noise figure. And this is absolutely important, because if you, for instance, change this value, then all the noise figures you determine are not comparable with noise figures giving from, let's say, industrial devices, from amplifier, from a receiver, and so on. Okay, then we have a connection between, or we can realize a connection between the noise figure, which is the capital F in our case here, and the so-called noise temperature. What is the noise temperature? In a lot of cases, especially if we have very, very small noise figures, means very small f's, then to make a better, or we can make a better comparison between devices which has very low noise figures. And if we talk about this noise figure, the large f, in a lot of cases it's given in log scale. F in dB means we have to make the decadic logarithm of this expression multiplied by 10. Then we have another scaling. And in case of small noise figures, it's a little bit, let's say, the values are stretched, and we can also compare this. We can discuss about a noise figure of, let's say, of 1.2 and 1.4 dB. Okay, then we can see in the tens value after the comma, we can see it's better or more worse. But for instance, in radio astronomy, they like to use the noise temperature. And what is the noise temperature? This is an equivalent temperature, again, of the real part of our source impedance, which delivers a noise, the terminal noise in a noise-free device. Means we assume that the noise, this additional noise or the added noise coming from the device under test, we assume that this noise is not produced inside our device under test. It's produced as a higher temperature of the real part of our noise impedance. We can, in our mind, we can think, okay, we can artificially increase the temperature of our source resistance, of the real part of the source impedance, and this produces at the output of the device under test the same noise behavior, the same relation what we can find here. Means this is another idea to look to the noise behavior of a device under test, or a chain consisting of different blocks of noisy devices. Again, starting with the antenna, then connected to a preamplifier, for instance, a mixer to make another frequency, to make the input frequency lower in a so-called intermediate frequency, and then our, let's say, demodulator detector. Okay, this is a normal used receiver block diagram. Sorry that it's not here in one of the slides. Wait, I look. There's another student coming in. No. Okay. Again, we can relate this equivalent temperature instead of the noise figure in this way. We can say, if we can increase the temperature of our source real part to such a value that we can ensure the same noise figure regarding its formula here, then to get related to the 290-degree environmental temperature or reference temperature, then we have found an equivalent temperature of the real part of our source impedance, so that at the output of our device under test we have the same noise relations. And then we can express this with the so-called equivalent temperature, noise temperature, instead of given the noise figure. means both has the same background, or both express the same noise behavior of our device under test. Okay, now let's have a look to first of this diagram here. What is shown here, I try to explain you that the reference temperature here is given with 290 degree Kelvin, or without degree only 290 Kelvin. This gives the noise figure because it's the reference temperature for the thermal input noise. And now what happens, for instance, if we change this reference temperature to other values, if we change the temperature, the reference temperature to other values, for instance, to smaller values, 100 Kelvin, 50 Kelvin, or 30 Kelvin, then we can see what happens with our signal to noise ratio. In other words, I could also write here a second axis, a second y-axis with f, with another noise figure. Here is only given the signal to noise degradation, means what happens. Okay, if we let's say go, and here this is nothing else than the other scaling for our equivalent noise temperature of our source, of the real part of the source resistance. In case of our signal to noise degradation, if it's 1, it's clear. Then in reference to 290 Kelvin, we can say that this is equivalent with an equivalent additional. This is an additional increasing in temperature of the real part of our source resistance, and this is about 75 Kelvin. Means the real part, if we increase the temperature of the real part of our equivalent, the real part of our real part of the source impedance, if we increase this value from 290 to a value which is 75 Kelvin higher, it's 365 Kelvin totally, then our device has an output signal to noise ratio for either 1, or with this equivalent noise temperature of 75 Kelvin. If our reference temperature is smaller, the degradation must be higher, it's clear. Then we have, for the same value, a signal to noise ratio degradation of, let's say, about 2.5 dB. And if we go to an extreme value, for instance, the reference temperature is only 30 Kelvin, then our signal to noise ratio degradation, it's in the near of 6 dB. This is only to show you why we have to ensure that our reference temperature in every case is given by this 290 Kelvin. Otherwise, and you can see this here, we make a very large error, and the measured noise figure or determined noise figure, it's wrong with this, for instance, with this deviation of the correct value. Now, this is written here again. And now let's look what happens if we have a cascade of two different noisy devices. What is with the overall noise figure? What happens? From purposes of convenience, we have here only the real part, or it's only, let's say, ohmic resistance, a pure ohmic resistance, which produces the input noise. It's only thermal noise. It's given by this value, Boltzmann constant T0, means this value multiplied by the bandwidth. Yeah, this B, it's at input of our device, but again, this B means not the bandwidth at input, let's say at the output or at this connection point of our source to the input, means it's the bandwidth of our device, because only this noise power through the device, through the given bandwidth of the device, can be active and can be occur at the output. The bandwidth here at this point at the output of our resistance doesn't matter, because it's very different in a lot of cases to the bandwidth of our device under test. The same is valid for the second stage. Okay, we have here two stages of let's say of amplifier cascade. First amplifier has a bandwidth. Normally I could write here bandwidth 1 has the power amplification G1 and produces inside the added noise power of N added 1. Then we have here, okay, it's only B, it's the bandwidth B, but we will see that we can set both bandwidths equal, because only the overall bandwidth is important. Then with the power amplification G2 and the inside added noise power NA2. Okay, amplifier 1, amplifier 2. What happens if we look to the overall noise behavior? Here we have our input noise, means only thermal noise, given with this formula. It's the same like here, it's clear. Then we have the first stage. The first stage amplifies the thermal input noise, this value, with the bandwidth given by this amplifier multiplied by G1. It's the power amplification of the first stage. And now we see at the output what is present at the output. Then we have the added noise from this first stage. And this gives, from this value plus this, the overall output noise power here on this level. And now this output noise power goes in the second stage. What happened in the second stage? The second stage amplifies the thermal noise coming from the first stage, was already amplified by G1. Okay, you can see here it's amplified also G1 by G2. We have the product of both power amplifications. And now we also can see here the bandwidth. Why? This bandwidth is the equivalent noise bandwidth determined over or through both amplifiers. If, for instance, the first amplifier has a smaller bandwidth than the second, then the overall bandwidth, it's, let's say, it's marked, determined by this first amplifier. Or if it's opposite, means the bandwidth of this amplifier is larger than the bandwidth of the second one, then the overall bandwidth is determined by the second one, and doesn't matter how large or how small the bandwidth of the first amplifier is. At least we have a bandwidth determined by the second amplifier, because this is smaller than of the first amplifier. And then this is the reason why we can only introduce only one B, only one equivalent bandwidth, because this is valid as an overall bandwidth. We look through both amplifiers, and the smallest bandwidth determines the equivalent bandwidth which occurs in this formula here. Okay, this is coming, or this part of the output noise power, it's given by our input, by our only thermal input noise power. It's shown here. Then from our first stage, we give to the input the output noise, the added output noise power, or added noise power coming from our first stage, and it's multiplied now by G2, by the power gain of the second stage. This is this additional level of output noise power, and now without multiplication of second stage, we added the internal noise power from the second stage. It's only n added to the added noise power second stage without amplification. And now we can see here, this is the total noise power output, and this is away from the input thermal noise power multiplied by G1 and G2. This is the total added noise power, and the sum, it's the total noise power output. And then it's clear, it's not shown here, we have the amplified input signal. This is nothing else than the input signal multiplied by G1 and G2. And here we can see that we have, let's say, a much worse signal to noise ratio at the output. It's not the same like at the input. To give you only an example, what happens if we say, okay, this is assumed as the thermal noise power at the input, means at the input we must have an environmental temperature of 290 Kelvin. And what happens if the environmental temperature is higher, or we make the following, we say, okay, let's beat the thermal input power 4 times higher than the signal power. And I make this primitive experience here in this formula. I divide the input signal power by 4 times the thermal noise power. That means the input signal to noise ratio, it's only a fourth. And what happens at the output, if you rearrange the formula, you can see it's the same. If you can write, okay, the input signal, it's only a fourth. The input signal power is only a fourth regarding this thermal noise power T, K, the T0, and the equivalent noise bandwidth of cascaded amplifier. It's okay, it's absolutely the same. At the first look, it's not directly visible in the formula, because we have here in the denominator the sum of this value, amplified input thermal noise power, plus the added noise power. Okay, then let's switch to the next slide. The output noise, this is the summary of what we have discussed. It's written here. The output noise in this case consists of the thermal input noise power amplified by both gains. It's G1 and G2 as a product, plus the first amplifier output noise. This added noise amplified by the second gain, the G2, plus the second amplifier output noise, or added, the second amplifier's added output noise. This is the N added 2. So the noise power contributions may be added since they are uncorrelated. And this is very important. We cannot apply this formula if we could, if we could detect, or if we could see, or if we could have a proof that the noise powers are correlated, which is other. And as long as the noise sources are independent from each other, then we can apply this formula, and also we can add the noise power 1 and noise power 2. again, the main point is that the noise sources has no correlation to each other. This is very important, otherwise this formula is not longer valid. And the output noise power now can be again written in this way. And here now we have the noise figures of our first amplifier or first device under test. And here we have the noise figure of our second device, of our second stage or second device under test. In our case, we had two amplifiers. First amplifier F1, second amplifier was F2. And now we can see what happens if we make a closer look to the overall behavior. The noise figure of the combination of both amplifiers can be calculated by a rearrangement this equation, and means then we can look to a so-called overall system noise figure of this two-stage example. We can also imagine 3 stages, 4 stages, and so on. And so if this means is the overall noise figure consisting of the noise figure of the first stage, as you can see here, it determines the procedure more or less. And now the second stage, the noise figure, it's -1, but this is divided by the power gain of our first stage. And at this point, we can make a first conclusion and can say, okay, if the power gain of the first stage is, let's say, very high, then the influence of the noise behavior of the second stage, it's very, very small. We can minimize it. And this is shown here in this formula. And we can go further and can say, if the noise figure of the second stage, it's in the same order like F1 of the first stage, but the power gain of the first stage is very high, then we can say the noise figure of the second stage, it's more or less neglected. Because if both noise figures are in the same order, then we can also reduce the influence of the second stage by a high gain of the first stage. This is, I think, it's a very interesting result. And now we can say, or in other words, we can, I mentioned it already, the calculation may be extended to n stages, cascade of devices, and we can express it as, we come back to Harold Freese. This is the Freese equation, the overall noise figure. It's expressed here as Fsys, system noise figure. And this part we know already, look here. And the other stages in cascade we can find here. And this is very interesting. You can see here the product of all power amplifications of the stages after the first stage. Means second stage is divided by the first power amplification, third stage by the product of the first 2 stages, and so on until the end stage. It's we have the product of all amplifications. But at this point, I must say, attention, because power amplification means not in every case that it's positive, means we have a cascade only of amplifiers. We also can have a cascade of an amplifier, then for instance of a filter, means a filter is a passive device, and the filter has not an amplification larger than 1. It has an amplification in brackets, an amplification of lower than 1. It has a so-called insertion loss. It has a loss. It's an active device. An active device, sorry, a passive device. A passive device has losses, and only for explanation, a band filter, a selective device, has losses in such a way, if the filter is very small in its bandwidth, and the smaller the filter, the higher the so-called insertion loss or its internal loss. This is a special rule, depends on a lot of things, and means at least that also one of the G's here in such a chain of different stages, this G must be or can be not a value larger than 1. It can also be a value much smaller than 1. For instance, 0.01. It's possible. And depends which stage has this loss. So it can very strong influence the system or the overall noise figure. Let's make an example. If the first stage here with G1, it's the same, it's this what I mentioned already, has a high power gain, and the second stage, the power amplification of the second stage occurs here, and also the third stage has a high noise figure, and this product goes in the direction of 1, because let's say here this is 100. The 100 here makes the noise figure of the second stage neglectable. The third stage has a higher noise figure. So in combination with the power gain or the small power gain, for instance, of the second stage, this occurs here, then this product will be smaller than G1. And so the very bad noise figure of the third stage, we say looks strong through, means can determine the overall noise figure very, very strong. And so we have to look really to the values of the noise figures itself, F1, 2, 3, for instance, and also we have to consider the power amplification, the G1, G2, and so on. And this is explained again in this figure here. Oh, let's switch back. Okay. What we can see here is the power output versus the source temperature of a linear two-port device. We can see here, if we assume that our input noise power, for instance, could be made 0, it's only in our mind, it's in fact, it is not possible. For instance, if we could make the source temperature to 0 Kelvin, it's an absolute 0 point. It's from physical point of view, it's not, we cannot realize this, it's only imagination. And if we could do this, then at the output of our device under test, for instance, active device means in this case amplifier, then we can measure or can detect the added output noise power. This is shown here. Okay, but the device under test, for instance, an amplifier has an amplification. And if we look to our source temperature, for instance, this over the S here, this should be 290 Kelvin. Then we can determine this point. We could measure this output power, but it's not only the added output power, it's the output power of noise as a sum of the power amplified input thermal noise plus this NA, plus the added noise. This is here. And now if we could determine, or if we could realize a second point of this line by creating a new source temperature creating a higher source temperature. And from a physical point of view, you can do this. For instance, you have let's say the source resistance, for instance, 50 ohm. It's pure ohmic. Let's assume it, and then you can heat it up, this source resistance, by with a heater, let's say of twice the value, and then you also increase this input thermal noise to another value. For instance, here it's valid for 290 Kelvin, and then we make it higher with heating up, with physically heating up the source resistance to another value, to a higher temperature, let's say to 400 Kelvin. Then our output noise power, it's increasing. And now we have 2 points, and with these 2 points in this diagram, we can determine the steepness of, or the slope of this line here. And you can see here what happens. The slope, it's given by Boltzmann constant. It's clear. It's given in our input noise power, and the bandwidth is also clear. It's given by the transmission relation of the device under test. And now we have here the power gain of our device under test. It's given here with a G index A. And so we can find also the amplification, the power amplification with this method. And now let's discuss a tricky method based on these things here. In practice, it's not very convenient to heat up the source resistance, let's say by fire or whatever means physical increasing the temperature. In the meantime, we have another interesting method to realize this, let's say, higher source impedance with a semiconductor device, namely avalanche diode. Avalanche diode creates more or less white noise, means a noise behavior over a very, very large frequency range. And based on this possibility to create, let's say, a higher source temperature artificial with the help of a semiconductor device, this new method to determine the noise figure of our device under test of our amplifier, of our receiver, we can apply the so-called Y factor method. Now, how it works? With a noise source connected to our device under test, the output power can be measured corresponding to the noise source on and the noise source off with this method. In this primitive discussion here, you can say, okay, we apply our noise source coming from the real part or coming from a pure ohmic resistance at the input, 50 ohm, laying on our environment temperature 290 Kelvin, and now we heat up. This is the second point. This is this temperature we measure at this point here, 290 Kelvin, and now we heat it up, let's say with fire, the ohmic resistor to a much higher temperature, and then we measure the second noise power at this point, and this is this one here. And the quotient is the so-called Y, normally given by this capital Y. This relation is the Y. And what we can do with this relation, what we have to know. Yeah, to make noise figure measurements, the noise source, and now we speak about noise source. We do not only speak about the real part of our source impedance. Now we speak about a device which represents for 290 Kelvin this pure ohmic part, and then it can excite, or it can make the artificial temperature of this ohmic resistance much higher. Again, this is you can realize this with the avalanche diode, and the relation between the source resistance laying on 290 Kelvin and to a much higher temperature, like for instance 4,900 Kelvin up to 9,500 Kelvin. This relation of this noise source avalanche diode, it's called excessive noise ratio. This is given here by this relation. The so-called excessive noise ratio given in dB, it's nothing else than the temperature of our new noise source, means our, let's say, artificial resistance here. If this resistance is hot, it's laying on, for instance, between 4,900 and 9,500 Kelvin. It's clear if you apply this temperature on the real ohmic resistance with fire, with a super hot flame, it's clear then such a resistance it's destroyed, it's vapored. You cannot do this with physical methods. This is the reason why we excite, or why we create this equivalent white noise with an avalanche diode, and not based on physical processes heating up this resistor. And this is the hot temperature laying in this interval here, minus this is our cold temperature. Normally the cold temperature, it's the same value like this here normally, but we make here a difference because it could be possible that if we switch off this noise source, this avalanche diode system, the temperature coming out from this device going to the input of our device on the test, it's different to the reference temperature of 290 Kelvin, and this is the reason why we have to insert here a T cold. But both temperatures in difference are related to our reference temperature of 290 Kelvin. This is visible here. Again, if it's identical, both temperatures, then we have here TH divided by T0 minus 1. Okay, this is the formula rearranged. We look for here the output noise power, and the output noise power in case of our device on the test, it's given by it's clear Boltzmann constant, reference temperature, bandwidth, the gain of our device here, and now we have measured it with the Y method. Then we have the excessive noise ratio. We have to determine this first, it's clear, together with our avalanche diode. And then you can see here the Y factor occurs only in this formula, displays only one time. Yeah, and so we can determine the internal added noise power of our device on the test. If the device on the test gain is very large, means if this gain is much larger than the noise figure of the device after our first device, then the noise contribution of the second stage will be small. This is what we already have discussed in this in the slide before, in one of the slides before. And again, the overall noise figure measured with the help of this Y factor is now expressed by this formula. Means we can neglect it under these conditions. The noise behavior of the other stages coming behind the first or coming after the first stage. We in every case we have to know this excessive noise ratio. Again, it's with this switch back. It's this relation here, difference between hot temperature rated by an avalanche diode, this noise value minus the cold value source is switched off and divided by our reference temperature. If it's identical, we have here the 1, and you find this value 1 here and here and here. Yeah. But for explanation, if, for instance, the noise figure of our device, what we want to measure, if this noise figure is much is much larger than this excessive noise ratio, then we cannot apply, in this case, this very tricky Y factor method, what we can use in a lot of cases for determine the overall noise figure of a complete receiver or to determine the noise figure of an amplifier. This is again shown here. This is the overall noise figure. We cannot determine the single stages. We only apply our avalanche diode as a noise source and input of this complete amplifier. And we measure only we determine the so-called Y factor. If we measure the output noise power of the complete cascade in case of noise source on, and the second measurement value is noise source off, and this is the Y factor, and then we can determine with this Y factor the overall noise figure without considering the noise behavior of the single stages. Now, if we cannot apply our, for instance, our Y factor method, because the noise figure of the device is very, very high, or it's higher than the so-called excessive noise ratio of our noise source here. This is, for instance, given in case of power amplifiers, means input amplifier of a receiver. It's normally selected after the rule. The noise figure should be as low as possible. And if we look to power amplifiers, means if we look to a transmitter as the last stage before the signal goes to the antenna, large radio stations, for instance, have power amplifiers which delivers not only 1 kilowatt, maybe 10 kilowatts or much more. Also transmitters for TV, earth stations, also power amplifiers installed on a satellite platform to amplify the TV signals transmitted to Earth. Then such power amplifiers delivers also, let's say, up to 200 watt at very high frequencies in the X band, for instance, between 10, 12 and 10 and 12 gigahertz, or at much higher frequencies in the so-called Ka band. It's in the range of, let's say, 24 up to 27 gigahertz and so on. Such amplifiers has normally noise figures which are much larger than noise figures of the input amplifier. For instance, if you have on the Earth, you have your receiving system for satellite signals, TV signals. You have a large reflector, means a dish with the low noise block in the focal point, and such an input amplifier of so a low noise block for satellite reception has a noise figure in the order of 0.7 dB. It's an equivalent. It's an equivalent noise temperature of, I think it's smaller than 30 Kelvin. This is very, very good. And the power amplifiers, for instance, on satellite platforms, in a lot of cases, we have there tubes, electronic tubes, traveling wave tubes, and they such power amplifiers based on traveling wave tubes has noise figures in the order of 25 or 30 dB. It's much larger than the common or normally used noise sources with an excessive noise ratio of, let's say, between 12 and 15 dB. Yes, this is about 12. It's, let's say, about 5,000 Kelvin up to 9,000 Kelvin, 9,500 Kelvin is the range of the equivalent noise temperature. And so if you have such a, for instance, such an amplifier and want to know its noise figure, then we can also apply another method, but this method you can apply also in case or instead of this Y method here. But if you have, for instance, such a device with a higher noise figure than the excessive noise ratio, then we can use the twice power method. Means we have a generator. In a lot of cases, we have a generator. A signal generator only delivers a sinusoidal signal, and this generator you can find it in each laboratory. We can use such a signal generator. What we have to know, or what we must have, is that the output power of such a generator must be very precise at very low levels. Means that if you reduce the output magnitude or the output amplitude of this generator, of this signal generator, it must have a very high range of allowed attenuation. Such generators can reduce the signal down to, let's say, down to minus 100 dBm or minus 120 dBm. Means to very, very, very small levels. Otherwise, we cannot exactly determine the noise figure of a receiver. In case of a, let's say, power amplifier, it's not necessary to go so deep with attenuation with the signal, but nevertheless, with such a generator, you can measure now the noise figure of a device. Yeah, how we can do this? We must look to the output power, the input signal of the generator's magnitude is applied to our, for instance, power amplifier. Then the input power is reduced to such a way that it doesn't play any role, or it has no influence at the output power and the output noise power of the amplifier. The amplifier is switched on, it's clear, and at the output we have a power meter. The power meter must be capable to measure also the, let's say, the efficient or the correct power of a noisy signal. And then we measure only if the power amplifier is switched on. We measure only the output noise power without an input signal. And what we have to do now, we increase the input power in such a way that our output signal is regarding the state before, goes up, for instance, to twice time. Means our power measure shows now twice the output power. again, first amplifier is switched on. At the output, we have a power meter, which can measure the output power of a noise signal. This is very important. And this power value we can notice. And then we apply our input signal with a generator and increase the input power of the generator in such a way that the output power is twice the value what we have measured before. And this value, let's say it's noticed. And we can, before we make this, we also can, we can determine the gain of our amplifier. We increase the input power in such a way that the output power it's far away from this first value what we have measured only with the output power, because this is the output power coming from inside of the power amplifier. It's our added noise power. And if we want to determine the gain, then we apply an input power in such a way that the output power is, let's say, 10 or 20 times higher than the added noise power. And then we look only to the quotient from the measured output power and the delivered input power. Only this quotient is our power gain. It's very primitive. In the first case, if we only increase the output power twice the added noise power, then this value it's not directly the gain of our amplifier, because we are in the near of this input or amplified input noise and the added noise. Because you look to the formulas, then you can see because of this summation, we cannot determine if we look to the output power, it's only twice the added noise power, and we look to what has our generator delivered. This is not the power gain. It's a wrong value. But to determine our overall noise figure, we can look to this value. We have to notice this value. And this is now related to our thermal input noise power. And we already know that the output noise power is much higher than input noise power multiplied by the power gain of the amplifier. Maybe such a power amplifier can have a power gain of 1000. It's 30 dB. It's not a problem. But again, the noise figure itself can be much higher than that value what we know from low noise amplifiers as input stage of a receiver. In our case, we speak about also of a noise in dB, of a noise figure of 30 dB, or in this case, fSUS. It's in the order of 1000. Okay, if we look to these relations, then it should be clear that the amplification of the thermal input noise, this value multiplied by the G of our power amplifier, it's in every case much smaller than the additional introduced or additional created noise in this power amplifier. And this is shown here, I hope so, in this slide. Wait, switch back. What we have to know is to apply this formula. This is we have to know, and now we can back to this equivalent noise bandwidth, the log B. Also, our power amplifier has, for instance, a bandpass characteristic. In a lot of cases, maybe more or less, or can have a low pass characteristic, but in a lot of cases, we have bandpass characteristics. And we cannot only measure let's say, the transmission curve of our power amplifier and to say, okay, the normal definition is we have the maximum, and to lower frequencies, and to higher frequencies we have 3 dB less, or it's 1 divided by square root of 2 less regarding the voltage. Regarding the power, it's the half power, the lower half power, the upper half power over the frequency. And between these 2 points, it's normally determined as bandwidth, only bandwidth. But here we have to consider not the bandwidth as a, let's say, as a transmission figure of merit, or a transmission figure value. We have to consider the equivalent noise bandwidth. And what does it mean? And this is shown here. Let's assume this is a transmission curve of our power amplifier. And now, first of all, we have to determine in every case, if we measure the transmission curve, we have to look for the maximum. This is the Gmax, this is the maximum power amplification of our power amplifier. If it has, it looks like a Gaussian curve, but it can also have another transmission curve, doesn't matter. Also, the transmission curve can have a ripple here inside. But in every case, we have to look for the highest point, means the maximum power amplification. This we have to determine. Doesn't matter if it's here or here, in this interval of, let's say, single frequencies, but we have to determine this value because we have to relate now the integral over the transmission curve to this Gmax value. And for the integration, we can do the following. We can measure our transmission curve, let's say in 10 or 12 or 8 or 9 discrete frequency values. And it's not necessary to hit the Gmax in this case. Although this discrete points, we can shift it to another value which lays between 2 discrete points regarding the Gmax. But the Gmax we have to again to determine, for instance, separately. Okay, now we have here a number of equal segments of integration. That all means we have n equal segments with different amplifications over the frequency. Made again 10, 12. The higher the number of the segments, the higher is the precision, the higher is the value of this determined equivalent noise bandwidth. And one integration possibility is this is the denominator. It's shown here. It's this is the formula. It's nothing else. At a single frequency is the G's added here divided by n, by the number of discrete values. This integration can follow the so-called rectangular formula rule, or we can use the trapezoid formula rule. Then we have here a little bit a difference because it's divided by twice the number of discrete values, and you can find here also all values between G1 and Gn are also multiplied by 2. And this it's in principle equivalent to this formula. It has only another approach. And what we can find, it's visible here. This is a rectangular. This area under this rectangle, under this Gmax, this gives us, after this rule here, the equivalent. This be the equivalent noise bandwidth, and this is let's say the key point of to determine the so-called equivalent noise bandwidth. If you have no time, then you can apply, for instance, this primitive Kepler's barrel rule. You only have to know 3 different values. Again, in every case, you have to determine the Gmax, the maximum power gain, and you can see it's used here.
And then you only have to know two different other values, a lower value, a higher value. And if you insert this power gains in the formula, oh, now the pointer is blocked. Yeah, then you can find it here, very, very simple. And again, the transmission curve must have, let's say, more or less such a shape. And if it has this shape, then the precision of this primitive method, it's in the range of about 5%. It's enough for a lot of applications. Yeah, and then at least in modern spectrum analyzers, as noise detectors, the equivalent noise bandwidth is available. It means the readout is already in, for instance, in dBm per hertz. It means it gives you the measured power of a single spectral line already regarding to the equivalent noise bandwidth. Means it's a noise density. The readout is the noise density. It's power per bandwidth per hertz. Okay, this is in principle the end of our lecture today. I mentioned already that we also have or want to discuss about the noise behavior or the noise relations of an antenna, because the antenna or every antenna is a passive device. It's clear, consisting of material, means consisting of conductive material, metallic parts like aluminum, like copper, like brass, and similar things. Or aluminum, I mentioned it. And this material has, in every case, a limited conductivity. The best value, it's is silver. Silver has, from all its metallic materials, the highest conductivity, but it's clear nobody will apply pure silver as an antenna material because it's very expensive. What is done and what you can do in practice, it's not the case. You can make a galvanic skin finish from silver. Then you can save this very expensive material, and you can increase the conductivity. But silver has the disadvantage that it reacts with some materials in the air if the antenna is mounted outside and not mounted, let's say, under a radome. A radome can prevent atmosphere influences to the antenna. But a lot of antennas are made from aluminum. Aluminum has a lower conductivity than copper and lower conductivity than silver. It's clear. And but in a lot of cases, it's sufficient to realize the antenna with aluminum. And aluminum has a high withstand against influences from atmosphere, from weather, rain, and so on. Okay, now let's switch back to the slide 43. And in this slide, I started already with discussion of noise behavior of an antenna, and I only want to show you the sources of, let's say, it's thermal noise. It's clear only thermal noise because it's a passive device of an antenna, and also thermal noise coming from outside in the antenna. Okay, we are here. Here you can see the single parts of the, let's say, thermal noise, influences, which determines the noise behavior of the overall chain. We have here the antenna. It looks like a one antenna. Let's assume it's a one antenna. Then here at the end of the antenna, over the length L, we have a transmission line. Also, the transmission line has losses, it's clear. And we will see in the formula that these losses also produce additional noise behavior, or you can also say it reduces the signal to noise ratio from the input to the input, from the input of the antenna to the input of our receiver. This is our receiver, and our receiver is given or is marked with not with the noise figure F receiver, for instance. It's marked or characterized with the equivalent noise temperature T, large T index, or like receiver. Okay, we only discuss this receiver chain, antenna input until receiver output, given with the overall not noise figure, given with the overall equivalent noise temperature of this receiver chain. Okay, let's start with the antenna. This was our main point. In this plane, we have an emitting source, let's say, coming from the sun, for instance. If the antenna looks in the sun, then you can measure it, that the signal, the output of the receiver goes up. This is the, let's say, the noise source, or the temperature, noise temperature coming from the sun. So now the antenna delivers at the output a signal from the emitting source. Additional, our antenna is laying or has an environmental temperature, we name it TP. It's a physical temperature of the antenna. Normally it's not exactly or cannot be exactly 290 Kelvin, because the sun can heat up the antenna of a higher physical temperature. And in the formula, this is expressed with this term here. This is our physical temperature, and this gives an equivalent temperature now, depends on this EA. This is the thermal efficiency of antenna. The thermal efficiency of the antenna depends on the material of the antenna. It's clear. If the antenna is made from copper or made from aluminium, we have different thermal efficiency. It's comparable with the conductivity of the material. Copper has a higher conductivity than aluminium, and the thermal efficiency of the antenna, it's laying between 0 and 1. And in our case, it's in the near of 1. It's not 1, it's a little bit lower than 1. So that this quotient is a little bit higher than 1, because it's, let's say, 0.995 or whatever. And you can see here that this additional noise contribution given by this T from the physical temperature at this plane here is a little bit higher than physical temperature. And now we go along our transmission line. The transmission line has losses in sinking in the plane of equivalent noise temperatures, means that we have to describe the losses with a higher additional equivalent noise temperature, and this is given from this plane here to the input of our receiver. This is the T antenna. It's given by adding all these contributions. This is our noise temperature, equivalent noise temperature at the input of our receiver, not at the output, at the input. And this is the antenna temperature. This is coming from the emitting source. Then this is coming from the physical temperature, laying which are the antenna has in this moment. You can see this here, and this is the term again what we have discussed. This is inserted here, and here this is the natural number E, and you also can describe it with the base of 10, but it's here described with the base of the natural number E. And here, this is the, let's say, attenuation constant of our transmission line. For instance, a waveguide or coaxial line, doesn't matter. This value, you can see here, this increases from this plane to this plane. It increases the equivalent parts of the antenna temperatures. Yeah, and here we have again, because our transmission line is laying on it's assumed it's laying on our equivalent or it's laying on our reference temperature, T0, 290 Kelvin here. This is also along this transmission line increased to this value. And all the sum of these single parts together are given already at the output of the antenna and along our transmission line at the input of our receiver. This, let's say, increased equivalent noise temperature as a measure or as another expression for noise figure. And now the overall noise figure is shown here. This is the receiver noise power. We notice here, this is now this artificial, coming from here, the artificial or equivalent noise temperature of our antenna. This is the receiver noise power. And the overall noise power of the system, you can see here, it's the sum of the equivalent noise temperature of the antenna and the equivalent noise temperature of our receiver. It's shown here. You also can, or you also could express this with the noise figure of the receiver, but here all things are expressed with the equivalent noise temperature, and this makes the usage of the noise equivalent noise temperature makes the overall noise behavior much easier, because you can only apply here this sum. And okay, multiplied with the Boltzmann constant and the equivalent noise bandwidth, you have here the output noise power for the overall system. Antenna, feed line or transmission line to the receiver input, and here also considering the noise figure or the equivalent noise temperature of the receiver itself. So now this is, let's say, the end of our last lecture. Again, I repeat, I will send you the lecture as PDF to your leader of the group when he knows my, or when he knows my, or when he can find my email address, and then I will send you immediately this slides, and I think additional I can send you the slides in Russian. Maybe one of the teachers in Kazan has translated all the slides in Russian. Maybe it's or it could be an additional help for you. But nevertheless, the exam in 2 weeks is in English. All the things are in English. and I will give you some questions. It's not only, let's say, a discussion in such a way that I say, please explain me this, please explain me that. We will make it as a, let's say, as a discussion between two engineers. I have a problem. I have antenna A and antenna B, and I have to make a transmission. And I ask you, please give me your ideas how to solve this problem. Yes, and we discuss and we try to find a solution between your knowledge and my knowledge. And so this is, let's say, how this examen goes on. And then at the end of, I think it's the discussion, it's about 30 minutes. And at the end of this discussion, we have to find a grade. Okay, this is, yeah, it's live. And this grade, I don't know, will be more or less, depends on your knowledge. What I want to say is that it's not necessary to know a formula, to write down a formula. So it's necessary to have a certain understanding what I have to discuss. For instance, let's stay here with this antenna. It's not necessary that you can write down me this formula. You can, if you can explain me how, let's say, for instance, this noise behavior comes together to the receiver and influences the overall behavior, then I can see, you have understood what happens in this situation, and this is sufficient. This is sufficient enough for the principal understanding of antenna. I guess you will not be an antenna designer, and so we have to stay more or less on the surface of this, let's say, of this antenna design, and to come more deeper, then you have to invest much more time. And additional, in a lot of cases, we have so-called development software or design softwares like HFSS. But I think I can give you maybe together with if I send you the slides, I also can give you a hint where you can find, if someone has interest, a free simulation software. It's a very good software comparable with HFSS, but HFSS it's expensive, or you can find a crack version, but this version is free, and it's from my point of view, it's very good as far as I could see it on the desk of a other colleague, and it's made by Polish scientists, and yeah, we will see. Maybe last year it was available. I don't know if it's available until now, but okay, if someone has interest, you can try to download it, or he can try to organize a correct version of, let's say, high level simulation programs like HFSS or Microwave Office. I don't know, I have forgotten the name. And yeah, but with these programs, you have a lot of possibilities, but it's only useful or necessary for, let's say, for professionals who has really to design an antenna and not for radio amateurs. If you want to only to check how a Yagi antenna works, or what can I do to optimize a Yagi antenna, then it's not necessary to use such high professional programs. Okay, so thank you for your attention, and then I wish you all the best in the outgoing semester.
and have a nice evening. Bye.
Goodbye.
Goodbye.